well, for this it doesn't matter, but I'll go ahead and indicate it anyway. Let's say it goes some distance L. I want some distance L, right? Not to be confused with angular momentum, sorry about that. Some distance L. And what else do I want to know? Well, I'll think of anything else we need to know. Okay, great. So we want to know what the acceleration is down this direction. Let's define this as our x-axis. Let's call this our y-axis. Okay? We don't have to do it that way, but I think that'll be nice because I know the motion is always going to be the center of mass is going to move in the x direction. It's probably a simple way to set the problem up. Okay, so what do we do? Well, whenever we have a problem like this, I shouldn't say whenever, but often when we have a problem like this, we'll use Newton's second law. So let's start off with that. Oh, before I do Newton's second law, what do I make? What kind of diagram? Free body diagram. This is a rotary motion problem. So what I will do is either make a fancy free body diagram or I'll make two free body diagrams. And by fancy, I mean one that actually shows the full object and where the force is at. That's really important when we calculate our torques, which we're going to have to do in a few minutes. So what I usually do is this. And on exams, I'll say, like on the last exam, you were asked to draw free body diagrams of a particular system, right? On the next exam, chances are I'll say, draw me a free body diagram, and if your diagram consists of a dot with arrows, then give me a second one that shows the full extent of the object. Give me an extended free body diagram. All I mean by that is that I tend to like, of the wheel, I tend to like to make two diagrams, one for Newton's second law and one for the Newton's second law for rotation. So how many forces are acting on this wheel? Yeah, three. I think it's three. So we got force of gravity, we got a normal force, and force of friction. Which way is the force of friction pointing? If it's rolling down the hill, which way is the force of friction pointing? Yeah, it's going to be going up the hill. So that looks like this. Force of friction. You've done this before. Same old thing. The thing that's new here is that we're also going to draw an extended free body. So I'll say free body diagram, wheel, and maybe I'll say extended or alpha for rotary motion or something. And what do I mean? I mean I draw a nice big picture of the wheel. I indicate where the forces are acting as well as what direction they point. So the normal force points that way. And where does it act? Where's the normal force acting? At the center of mass? The very bottom of the wheel? Almost. It's not acting at the very bottom. It's acting off a little bit over here, right? The normal force is acting where the wheel meets the road, right? Or the ramp. That's where the normal force acts. So I'm going to draw a really careful drawing. And I'm going to line everything up. Say, okay, here's, I usually put a dot to indicate where the force, just so I can read my own drawing. Here's where the normal force acts. It's going that way. Force, normal. Does everyone see that? So I got my normal force pointing. And notice it's pointing right at the center of mass. Why? Because it's a round wheel, right? Center of mass is in the center of the wheel. This normal force is perpendicular to the tangent to the wheel right here. So it's really a radial force. It points right at the center of the wheel. That's important. What else do we have? We have the force of, I'll put it over here. Well, we have force of gravity. Where does the force of gravity act on the wheel? So that's almost a trick question. Where does it effectively act? Like one person's saying it. Come on. Do you guys not know? Who does not know where the force of gravity effectively acts on the wheel? So, okay, so the force of gravity actually acts everywhere on the entire wheel. This little bit of mass, this little bit of gravity, this little piece of mass. So we could draw a free body diagram that's got thousands or millions of little vectors everywhere, and that would be a very honest picture of what's happening. But it turns out mathematically, using Newton's second law, we'll get the same answers for everything we have for a rigid object if we just go ahead and concentrate all that force of gravity right at the center of mass. So what we do is we draw a little dot center of mass, and we draw a downward. I mean, the dot's not important. I just do that so I can read my own, just so it's easier to see. But this is my force of gravity. Force of gravity points straight down, and it acts exactly at the center of mass. Very important. There's a third force in the problem. What is it? Force of friction. Where does that act? Not the center of mass, right? It's also a contact force. It's right the same place that the normal force acts. It goes up the hill. So it's like this. So there's my force due to friction. And just to keep my head clear, I'm going to put an S because it's static friction. So it's not sliding, it's static friction. It's rolling without slipping. So this is the free body diagram you should get comfortable drawing now. We're into the part of the class where objects have physical extent. They're not just point objects anymore. They're not just sliding without friction either. There's friction involved. You've got to worry about where the forces act as well as what direction they point. Not just to get full credit on part A, but just so you can get anywhere past part A and the rest of the problem. You have to know where the forces act, how big they are, and what their angles are with respect to the horizontal and vertical. Okay, great. So I've got all my forces. Now what I'm going to do is I'm going to solve Newton's second law in the x direction and the y direction, and I'm going to look at the rotary motion version of Newton's second law. Should I do it on this board? Here, I'll do some of these things on this board and I'll do some over there. So the first equation we need, let's do it on one board so the camera's got it on one board. Here, let's do this. So what do we do? First thing we do is Newton's second law. And let's do it in the x direction. That's going to be the more interesting one. Newton's second law in the y direction is not going to give us anything useful, right? So in the x direction, what do we get? Well, I've got my positive x direction. Well, I've got net force in the x direction equals ma sub x, right? What is net force? Well, there's the gravity force in the x direction, and then there's the normal force in the x direction, and then there's the force friction in the x direction, and that equals mass times acceleration in the x direction. And what do we ask for? We were asked for a sub x. So this is what we're looking for. So we're looking, that's good. We've got an equation with the thing we want. But we've got some unknowns here still over here. So let's see. What is the x component of the force of gravity? Let's see. Well, let's draw a diagram, right? Let's go back over here again. I've got my downward force due to gravity, and I'm going to break it up into components for x and y. I'll do that. It's a triangle you know well. This is my angle gamma. Does everybody agree with that? Did I screw that up? I know that I got, so if this is my force of gravity, it points straight down. I know that for angles on the opposite, well, it's opposing the longest vector, the original vector, force of gravity. I know that the small angle better be gamma. This is perpendicular. Okay, good. That's right. And what am I looking for x? I'm looking for this piece right here for x. What is that? That's going to be sine of gamma as I defined it. So it's force of gravity. I'll just go ahead and write it mg times sine gamma. Very good. It's a terrible gamma. You know what I'm trying to say. All right. Super. So force of gravity, is it positive or negative, given my conventions for x-axis?
Positive.
I think, yeah, positive. I think you're right. So it's positive, and it's mg sine theta. Oh, sorry, mg sine gamma. Now, normal force. Does the normal force have a component? Yeah, in fact, the normal force is going to have a component. Oh, no, is it? Well, actually, wait a second. Normal force is vertical, right? Yeah, it's perpendicular to the x-axis. So what is the normal force component along x? It's 0. I'm telling you it's going to be non-zero. All right, 0. What about the force of friction? Is that a non-zero component? It does. Is it positive or negative? Now, suppose you didn't know at the outset of this problem which way, this comes up all the time, right? If we didn't know at the beginning which way force of, the friction force was pointing, we took a guess. You did it this way. I would carry that guess through. I would say now what you all said. And if I got a negative number at the end for the force of friction, the length of the vector of force of friction, I know that I made the wrong guess in the beginning. We guessed right, so it means that we're getting a positive number if I don't make an algebraic error. So good. It's pointing that way. That means it has a negative x component. And it's the full length of the force of friction vector. There's no trigonometric issue because it's pointing exactly opposite direction of s, right? So I'd say it's negative f sub friction. But I don't put an x component here now because that negative sign took care of that, right? Like up here, this thing is negative that. This is the length of the friction vector. That's its x component, right? That's anyway. You've seen this many times. Great. So now I've got m times af. So this is nice. It's got the thing we want. But we don't know the force of friction. We don't know what the magnitude of the force of friction is. You have to solve for that, and then substitute it in to figure out what the thing we want to know is. We do know everything else, though, I think. So we've got one equation, two unknowns. Now, if you do Newton's second law in the y direction, what do we get? I think you can probably guess what we're going to get. We get mg cosine of gamma, right? Because that's the hence negative, right? Plus the normal force equals mass times the y component of acceleration. What is the y component of acceleration of the wheel? 0. Because the wheel's not flying up in outer space or going into the, it's staying on the ramp, right? So this is going to be 0. Okay, well that tells us what the normal force has to be. It's going to be mg cosine gamma. But that doesn't help us solve the problem we're trying to figure out, right? That doesn't help us find a sub x. So we have two equations and three unknowns. Doesn't help. All right, so what do we need? We need another equation. Well, let's do Newton's second law for rotations. That's our new equation, right? What does that tell us? Well, it says that torque net, okay, this is really important. This is the thing that a lot of you are, like, the next midterm, people are going to have to know how to calculate net torque, and many students will not learn how to do it if past semesters are any guide. This is going to be different. It's going to be different this year, right? Like, everyone's going to learn it. People are going to find out how to calculate torque. So let's calculate right now. What does net torque mean? Same thing as net force in the sense, the net has the same meaning. We're going to add up all the different torques together and get a net torque. So net torque equals what? It equals I times alpha. I didn't screw that up. F equals ma, torque equals I alpha. Okay? Oh, what else would we be given? We better be given I, or at least be told what kind of wheel we're talking about. You have to know the mass distribution of the wheel. You want to do any integrals on my exams, but you'll have to know, the problem will probably specify I explicitly. And there's a lot of different I's you can have for any given object. So let's say that it tells us the center of mass. Let's say it gives us I center of mass. It tells us what the moment of inertia is about the axis of rotation that goes to the center of mass. Yes? Did I get it wrong? So this is, you agree with the magnitude, mg cos gamma. The reason it's negative is in the y direction. So where's my y direction? My direction points that way. Gravity's pointing straight down. The y-axis points up to the right. So it's true that it's not exactly opposite direction of gravity, but it's more opposite than in the same direction. In other words, if I break gravity into two components, as I've done right here, which way the arrows have to go in the two components to get from here to here? Well, first I go this way, and then I go this way. So that means it's positive along x, because x is positive, and this, x-axis goes that way, but the y-axis is this way. That's opposite direction. Does that make sense? So you get a minus sign for this. You've seen it before, but it's good to be reminded. Yeah, and keeping that kind of stuff straight is huge for making sense of when you're halfway through the problem to make sure things are working. So yes, thanks for asking. And then if you actually, this is 0 here, so then if you swing the next step of the algebra, you get positive mg cosine gamma equals positive s of n, right? And that makes sense. So yeah, I think I got the sign right, but thanks for checking that sign. So what is the net torque? Well, it's the torque due to each of the individual forces added up. There's a torque due to the normal force. There's a torque due to gravity. There's a torque due to, what else is there? Friction, right? And that all has to equal I alpha. Okay, let's evaluate each of these individually. And this is the trick. This is what gives a lot of students trouble. We're going to separately calculate the torque due to the normal force right now. Well, and there's our formula for torque. It's just F times that R vector, whatever that happens to be, times sine of beta. And there's a different beta for each of those three. We have to figure out what it is. So here's our picture of the wheel. Here's our normal force right here. It's acting right there. Oh, and what's our pivot point going to be? And what's our direction for positive rotations? So there's something I need to tell you that I think the book does not explain very clearly. I don't think the book even says it in there. Very important fact. Our book is great and it makes things simple, but sometimes it's a little shy on the details. So when you choose your pivot point, you've got two legal choices. By legal, I mean that'll give you an answer that's correct. I'll put it right here. Where will I put it? I'll put it up here. Right here. So allowed pivot points. Any stationary point is allowed to be a pivot point. What do I mean by stationary? I mean a part of the object that's not moving at all. So suppose I had a wheel and I put a nail through the center of the wheel. I would never do this. I put a nail through the blackboard and spun the wheel around that, or whatever. That's the wheel. Maybe I'll take this piece of paper. Okay, now I put my finger there. I'm holding. The part that's not moving is where my finger's holding onto the wall. That's a stationary point, the piece of paper. That's a legal point for my pivot point. And in fact, it is pivoting about that point, so you can see why they call it that. But it's not the only choice you can make. You can also choose the center of mass. Okay, center of mass. That's always a fair choice. It's always a legal choice. And when I say legal, I mean that if you then use that as your convention for your pivot point, Newton's second law for rotations will be true. If you use some random point in this object, suppose you have this, I got my piece of paper, it's moving around like this, and I take some point over here that's not a center of mass, and it's moving. And I plug in Newton's second law for rotations, I'm going to get crazy answers that don't make sense. So you only have two choices for a pivot point. Either the center of mass of the object, or any point on the object that is not moving. And it's okay if it's only not moving momentarily. Strange as that sounds, but that's okay. So that's your choice. And of course, you also have to define your positive sense for rotation. So let's choose a pivot point. I'm going to go ahead and label it. So back to this board. I'm going to label it on my free body diagram. You don't have to. You can label it somewhere else. You better label it somewhere so the grader knows what you're talking about. And so you know when you go through the problem. Let's make the center of mass our pivot point. Okay? That's my pivot point. What's my direction for positive rotations? I like to make clockwise positive, but it doesn't matter as long as you stick with your convention. So I'll do this. I'll make a little sign right here that says clockwise, and I'll put a little positive sign in quotes. That's my symbol for myself. It says positive rotations are clockwise. And I need to stick with that convention when I'm looking at omega, alpha, theta, torque. All those things have to agree with my notion of positive sense of rotation. For the same reason that when you define your x-axis, you have to define your velocity, your acceleration, your position. All those things have to conform to the fact that the x-axis has a positive direction. You can't mix it up, right? Your forces, right? All those things. Great. So now we've got our convention stated. Now we can calculate each of these torques. How do we do it? So for the normal force, I'm back to this board again. We've got our normal force right here. It's pointing, well, it's acting at this part of the wheel. Here's our pivot point. So what's our radius vector going to be? It's going to go from this point here, the pivot point, to where the force acts. This is r in that equation for torque. What is the length of r in this problem? What is the radius of the wheel? I call it capital R. Well, it's capital R. Bob your uncle, right? Here. So there's capital R. Now, the torque is going to be that distance capital R times the length f sub n times what angle? Well, f sub n is pointing in the exact opposite direction that r is pointing. Does everyone see that? R is pointing from here to here. F of n is pointing from here back the same way, the opposite way the r is. So the angle between them, beta, for this, is 180 degrees. Pi. What is the sine of pi? 0. Another way to say it is, what's the radial arm for this force? Well, 0. It's pointing right. It's like trying to open a door by forcing the door toward the hinge. If you grab the doorknob, right, and you push it so that the force is directed at the hinge of the door, the door's not going to open or close. You got 0 torque. I don't care how hard you push, you're not getting any torque. Why? Because the sine of 180 degrees is 0, right? So that means that tau sub n, the torque of the normal force is, well, to be pedantic, I'll say it's capital R of the wheel times the length f sub n times sine of 180 degrees. So this whole thing is 0. Okay? How about the torque due to gravity? Where's gravity acting? Gravity acts at center of mass. Where's our pivot point? Center of mass. So what is the length of this, of the r vector that goes from the pivot point to where the force acts? 0. So we didn't even get far enough to even calculate sine of whatever it would be. The angle's not even well defined because one of the vectors has 0 length. You got a 0 length vector. Well, 0 times anything is 0. So what do you get? You get 0. So this is beautiful. We set up our conventions for this problem in a smart way because I've solved this problem 20 times. Right? So that both the first torques here are 0. That's nice. Yeah. Yeah, the torque due to gravity is 0 because the radial arm is 0. It's because the force of gravity acts effectively at the pivot point. So it's like you're trying to open the door and you put your hand on the hinge on the door and push on the hinge. Door's not going to open. Might hurt your hand. Door's not going to open. Whereas over here, you actually, this force, this normal force is actually acting far away from the hinge, far away from the pivot point, but it's pointing directly at the hinge. So that's why that one's 0. So these are both 0 for slightly different reasons. Now, what about the torque due to friction? So that's why you have to have friction in this problem. See how much torque that survives, right? So what is the torque due to friction? Well, first of all, is it positive or negative? Take a look at this diagram. How do I figure that out? The way to figure it out is to think if the only force acting on the wheel were this one force in question, which happens to be force of friction right now, would it tend to make the wheel spin in a positive sense or a negative sense if you put a nail through it right where the center of mass is? Positive. So this problem is particularly nice in that this is the only force that's having any torque on the wheel. So the actual direction the wheel is rolling, the sense of its rotation, its clockwise sense of rotation, is in fact the same for the net torque as it is for the torque from this one force. That will not always be the case. You'll have problems where you've got 3 non-zero torques acting on some object, and one of them goes this way and that one goes that way, and you'll get the signs right. But it's just like net forces. Keep your wits about you. If you got 3 forces acting on a body, one force goes that way and 2 forces go that way, get the signs right, and it'll work out. Yeah. You're right. You can choose. So I just chose this to be the positive direction for rotations. It was my choice. It's just like choosing your x-axis. If you wanted to solve this whole problem with the x-axis being horizontal or pointing up the hill or being whatever you want, that's your choice. But stick to your convention. So if I use this as positive direction, then I better get a positive sign here for my torque due to friction. And what is the magnitude of it? Well, it's acting at a point that's a distance r from the pivot point, so I get capital R. The magnitude of the force we don't know yet. We have a name for it, capital F sub fr, right? And we also know the sign of the angle between these two forces. What is the sign between these two vectors? What is the sign of the angle? What is the angle between this a vector that points this way and a vector that points that way? 90 degrees. What's sine of 90 degrees? 1. So it's a very polite problem. I have to get sine of 90 degrees. 1. Great. So this survives. It equals I times alpha. Okay, now we have 2 equations, right? What do we have? This is our first equation. Yeah, we have equation. No. This one's not going to help us. This is the equation I want. We have this equation, and now we got this. We have 2 equations. But how many unknowns do we have? We have this, we have that, and now we've got alpha. We don't know alpha yet. So we need one more equation. We need an equation that's going to relate alpha and what? A sub x. So what is that equation? Well, if this guy's rolling along, right, the center of mass is moving in the x direction. What is the relationship going to be between the acceleration of the center of mass and the angular acceleration of the wheel? It's the same one we got up there, right? That a sub x equals some radius times alpha. In this case, capital R is just the same letter even, right? It's exactly the same formula. You have to be careful about the sign, though. Let's make sure the sign is correct. As this guy rolls down the hill, it's going in a positive x direction, as I define my x-axis, right? And it's also rotating clockwise. So that means that you get a positive sign in the relationship between alpha and a. So a sub x for this problem is positive r times alpha. Does everyone see that? So someone asked a minute ago, well, can I define the rotation stance to be positive in the counterclockwise direction? Absolutely, but then you get a minus sign right here. So just be consistent. Great, so now we've got 3 equations and 3 unknowns. Does everyone see that? So let's plug it on and see what we get. If we do that, you say, all right, I've got, whenever I see alpha, I can just stick in a sub x. So this is just equal to I a sub x all over r. Okay, that's combining these equations right here, 3 and 2. And now I combine that with 1, what do I get? Well, let's see. What do I need to get rid of? I need to get rid of the force of friction. That's the thing I don't know. So this thing allows me to just isolate that pretty easily. Force of friction is equal to that minus this. If I plug that into the bottom equation, what do I get? Oh yeah, no, these look worse than it is. These are 0 over here, right? So what do I get? I get, yeah, I might just, I've been doing this all nuts to me. I'll grab this to make sure I'm not missing something. I don't think I am. All right, let's plug it all in. How much? Let's do it in a couple steps and blow it up. Let's go ahead and isolate force of friction from equation 1. Right? What does that tell us? It tells us force of friction is equal to mg sine gamma minus ma, right? And now if I put that into my equation 2 and 3, that combined equation I got, what does that imply? That implies that, let's see, r times f friction, so r times f friction times 1. So it's just r times this, mg sine gamma, right, minus ma, if I didn't mess that up, equals I times ax over r. Is that correct? Am I missing anything? I think I got all my terms here. And now I've got a single equation with only one unknown, which is the thing I'm looking for, a sub x. And so let's isolate a sub x. See if I can do that. So a sub x, what does it get? It gets a minus r times m, and it gets, and if I put this on this side, I get a minus I over r. Well, it's fast and loose now. And now I'm going to add to both sides, I'm going to subtract to both sides of this stuff, so I get a minus, put minus signs everywhere. Mg sine gamma. Does that look right to everybody? I think that's got everything in it. Does everyone agree with that? Look at that. So now, this is looking good. I'm getting positive signs everywhere. I know when I'm done, I better get a positive acceleration, for x. Because we know the thing rolls down the hill. It doesn't roll up the hill. So that means it must have positive